Thank you for attending this reading group lecture. So today, the topic today is bridging 2K mode of mathematical reasoning. So perhaps, okay, so thanks. And today I'm going to discuss two papers. One is from Hermann Weyl. He wrote a paper, which is a lecture given about 90 years ago, say there are basically two ways to think mathematically. One is abstract algebra, means how can you bring things together, and another way is topology. I will give details later. Is what is the thing inside the pieces that you want to bring things together, and why I do the reading group today, because recently I read one paper is from Dr. Bradley. She bring information theory to connect these two mathematical subjects. She said, in her work, she proved that entropy function can bridge algebra and topology. But so I will first give you the background, the context of what is the thought of Hermann Weyl. So one question. So I guess everyone you know Hermann Weyl. Who is him? So he's a German American mathematician. He's a student of David Hilbert. Then in 1932, he gave this lecture about there are two mathematical thoughts. So what is his thought? His thought is that how people do reasoning, how people think, how mathematicians think. There are two ways. They always want to achieve one goal. Is this called true Dirichlet principle? In his paper, that people want to conquer a problem that using minimum computation, but can give maximum insight. How to do so is, once you do computation, you want to say, if things is well defined, then you don't need extra computation. And given maximum insight thought is within this, within the small entity that you are going to compute, you have maximum understanding of these small things. So for example, the real number system, we know real number system from building from the integer, the natural numbers, and then the rational numbers, because rational numbers is still not complete. People build the real numbers. But for the real number system, you actually have two perspectives to look at it. It includes both called algebra and topology. From the algebra point of view, in the real number system, each number you can apply addition and multiplication and their inverse, like the subtraction, like the division, these things. Everything is complete in this real number system. This completeness means that once you understand x times y, x plus y, you understand this operation plus or multiplication or division or subtraction. You don't care what is x and y, because this operation fully defines your understanding. Another perspective is topological understanding. To understand the real line system topologically, you see there are many beautiful properties. One is connectedness. There is no holes between two. There is no holes for an interval in this real line system. Unlike the rational system, there are holes like, for example, 1 divided 2 and 1 divided 3. There are many holes inside. Irrational number, transcendental number. Then, but with these two perspectives, you can understand everything about real number systems. For example, for irrational number, the square root of 2, you can understand it as an algebra of square root of 2. Then, if you try to understand the what is 2, if you cannot write it, for example, if you cannot write it like a hello. Okay, so if you cannot write 2 in a float number system in your computers, actually you cannot, because in float number systems you have a lot of digits for the integer part and a lot of for the decimal part. Then perhaps in the computers you will represent 2 as 1.9999. It's a limit. It's not exactly 2, but because of this closeness defined by topology, 1.9999 equals to 2. Then in real analysis, you can do calculus, you can do derivation, and to analyze these real number systems. So perhaps this is less interesting. Which is more interesting is when you go to college, go to university, you will go beyond the basic algebra, basic arithmetics, which later people calls abstract algebra. Abstract algebra focuses on the idea that you can do algebraic operations, but you don't care what it is. What is the entity you are working on? For example, here, when people consider the polynomial algebra, like you can say the polynomial of x can be written as the multiplication of two separate polynomials, and until you reach the irreducible polynomial. For example, I'll give you 2 examples because these 2 examples gives this multiplication into a different topological system. One is the quadratic form x squared minus 2x plus 1. You can easily separate as the multiplication of 2x minus 1. This is very simple. It's reducible in even this is reducible for, like, let's say you're in high school, you know how to do that. But perhaps in high school you would think this x squared plus 1 is irreducible over this real number system. But once you jump to complex number system, where complex number is defined on the complex domain, complex planes, and it can be written as x plus I, x minus I. This is factorization. Why is so? Because Cauchy actually introduced a polynomial, an undefined polynomial. This E is undefined, but he said we don't care what E is. E squared plus 1 is 0, and whatever 2 polynomials, if their difference is divisible by E squared plus 1, you assume they are the same. It's really like this modulus operation, right? This you consider the group modulus operation for all the numbers. For example, modulus 3, then 7 modulus 3 is 1, and 4 modulus 3 is 1. What Cauchy did is he introduced an undefined variables. Then what it brings is that you can do algebra by separate x squared plus 1. By say it can be written as this. It can largely facilitate your further operations. You may say, okay, it's nothing here, but in next slide you will see something different. In complex topology, in complex number system, there are many beautiful properties. When people study the complex plane, one very important property is this called Cauchy integral system. I guess you've learned it in first year of university doctrine. Says for an arbitrarily closed region. For this curve, once it is holomorphic and simply connected, means there is no holes inside. If there is holes inside, you will need these residue theorems. Then the topological property set, you can move them flexibly. this curve. So this curve is not necessarily being rigid. It can be flexible. You can continuously transform it. And if there, as I said, if there is holes or called singularities, you can apply residue theorems. But how to do that, how to combine these two is look at this case. Once you want to do contour integral over this blue curve, a blind computation would say, okay, we just cut it into a lot of small pieces, compute the integral of each small pieces by approximation like Riemann or Lebesgue integral. Then you sum everything together. Then it's very inefficient, and you won't do that. What you do is first factorization. Then you apply Cauchy integral formula because for Cauchy integral formula, any integral of this form z minus e. This is looks like a linear formula in complex domain. So the left hand side is algebra. You know how to separate a big thing into small pieces. The second thing is Cauchy integral formula. This formula is named by Cauchy, so you know it's not easy for us. It's not easy for us to understand the topological property of this complex domain, but Cauchy did that. We can use that. The thing to do is using.
Just sorry to stop you. We are on remotely. We do not see what you are doing. So Francois or someone else, can you turn your PC to show what Guodong is doing?
Or maybe Guodong, you could show what you show with the mouse instead of with the pointer in your computer to show the place.
Is it writing something on the?
No, not really. It was just showing things on the screen. So
Okay, okay.
The point with
it was not clear for me.
Should be okay, I think. Okay, could you do that?
Okay.
If you need to show some to.
All right. Perhaps I can start the video, and you can.
I can take those. That's a camera. I have a very good camera.
Yes, Guodong, you can use your camera and just if you show on the screen, well, it will be okay also for us.
Green help me to adjust the direction. Okay, can we go ahead?
Yeah, go, please go.
So
good.
To follow up what we just described is the left hand side is factorization, is algebra reasoning. You split a big equation into two pieces. The second thing is topological. It's based on the understanding of the complex plane. Because for all the complex plane, it's hold. You can change this a, you can change this function, but this Cauchy integral formula overall it's hold. Okay. Yes. So in practice, how we compute this contour integral z over z squared plus 4 is that we use two steps. One is the Cauchy integral, the Cauchy integral theorem to say this curve, you can flexible move it. You can introduce one, go over here. Once they are symmetric, it's the same. Then the next step is you can separate them. You can separate, you find the pattern of the denominator z minus 2i or z plus 2i. And this numerator can be written as the complementary part. And then you can directly separate this integral as the sum of these two. Then using the residue theorem, you can easily compute the result. So why this is important is this Hermann Weyl said, the mathematical analysis is a combination of these two. It's not relies on either A or B. Is that you always think how can you maximize your understanding. You maximize your understanding of algebra by finding the factorization. You maximize your understanding of complex plane by learning the Cauchy things, Cauchy integral formula and Cauchy integral theorems, etc. We are not, it's fine here. So yeah, so next step is we are going to the next paper, a course written by Miss Bradley. At the beginning, Miss Bradley said, he also mentioned this fact that there are two perspectives of mathematics. She quoted from Freeman-Dyson said in 2009 said, some mathematicians are birds, others are frogs. And while birds can fly high in the air and see the overall global views, they are very happy when they can unify the thinking, bridging the diverse problems together. And another way of think is a frog way of thought. They say the flowers and that grows nearby and they are very happy when they understand the details of particular objects. Then you see these two lines of thought are complementary. While Bradley didn't mention Hermann Weyl, but I think the Hermann Weyl part is important. And the most important part is not mathematical discussion, because what we are interested in is information theory, because we are a telecommunication, we work in telecommunication sector, and we highly rely on the entropy formula. So Ms. Bradley began with a question is how people organize information, just as the algebra thought, topological thought, and is how people organize information. For example, if you want to make a decision of choosing food, you assign a preference over cereal, oatmeal, fruit for the breakfast. You assign your preference for pizza or stir fry for your lunch. Then every day you make decision about breakfast and lunch. You say, okay, each time you make decision, you flip a coin, because the frequency for breakfast and lunch, you assume they're equal. Then you would ask yourself about your preference overall for this food. You will combine them. You will combine them. Then this is an informal description of probability or organization of information. How about goes formally? Formally is we actually have an entropy. We measure our preference. We measure the preference over breakfast, preference over lunch, and preference over the two. We can measure them by a number called entropy. Then the entropy, this is a well representation by a planar rooted tree. Say there are n elements. There are n elements are connected together by, say, this n things is once you make one decision, you decide between these n objects. Then you assign probability over this distribution. Then given this planar representation, you would say we can define entropy over this probability distribution. This is a classical definition for the discrete entropy. So for the moment, and in this talk, we don't talk about the continuous entropy. But yeah, so you see, you can have a number of this entropy. But what is an observation from Miss Bradley is she saw entropy is not a single number, but as a function, as how you see random phenomena. He say so record the definition of function. You map from one set to another set. It's definition of function. So for discrete distribution, like if there are two cases, each one is half. This is an element of the set delta 2 is two-dimensional simplex. Look at here. It means the entropy map this line from this line to a real number. For three-dimensional probability distribution, it's really like the entropy function can map this triangle into the real domain, assign it a number, and in fourth is the same. So once you see the entropy as a function that maps something like this to a real numbers, you can begin to investigate the property of this function rather than the value you have. That's an amazing idea observed by Dr. Bradley. Then we come to this idea to say, in fact, in our real life, we compose information. This we call that this is the preference over lunch, pizza or stir fry. This is a preference over the breakfast, like the cereal or something. And this is the case you are studying your pattern over breakfast and lunch. Then you get the overall preference over your eating behavior. That means you compose these two things and got an entropy of that. You can compute the entropy of that. One thing Dr. Bradley observed is that how to compose that is very interesting. This is called operad. Operad is within, perhaps it's better to move into previous slides. Once you look at each object, it is actually a topological mathematical space. You can study the behavior of over all the points within this triangle, within this line, or within this I forgot the name. Yeah. So this is the topological aspect. And this slide is you can compose that using the algebraic way of thought to compose them. It's really like our everyday life when we say like yellow banana. Yellow is an object of the color set. You can, when I learn English, you actually learn everything about color. Then you learn the banana. Banana is an object of the fruit side. You learn everything about fruit. Then in everyday life, when you convey information, you compose them together, right? You say it's a yellow banana or green apple or something like that. And up to this step, we say you can compose information, compose the distribution over in previous slides, mathematically it's called simplex. So you can compose the simplex using the algebra notion called operad. It's just a combination, but why this combination is important is pointed out by okay, this is the definition of operad. I put it here. It's a collection of abstract operation when you compose things together. If you remember, we do the factorization in the complex analysis part. You see, when these things is well investigated, these things is well investigated. You know the composition is well investigated. So this representation is algebraic. Then the very interesting observation made by Dr. Bradley is the chain rule of entropy. Is that the entropy follows a pattern. It's called the chain rule. When you compose this entropy, when you compose the distribution using this operad, you compute the entropy. It's indeed is written by the entropy of this node by the constant multiplication over the entropy over each leaves of this tree. This is the chain rule. The chain rule means you can organize information in serial style, like we said, yellow banana. It's a chain rule, right? It's a chain of information. And this is not going to be proved. Otherwise, it would take more than 1 hour.
P1, P2, Pn.
This P1, this P is the distribution of these leaves.
Is it not Q1, Q2, Qn?
Sorry for the definition. This Q is these things together. Okay. And this P is the value of this node.
K is you choose branch K, and then Qn is what you do with
okay, yeah. It's Q1 is the distribution of all these.
Yeah,
okay,
all the trees.
Right.
Yeah. Yes. Okay. So we come back to the discussion. And Ms. Bradley said one important statement that the chain rule is important because the entropy function is the only collection of functions that satisfy these rules. That's why entropy is so well behaved in organized informations, because otherwise you cannot find a better rule to define the information content of this tree.
For the record, actually, when Shannon defined entropy, this is the exact property he wanted to achieve. And he says in the original paper, yes, I want to have that. I can only do that if I do a P of P.
Yes, thanks for the comment. And when we call the Leibniz rule, we actually refers to the Leibniz rule of derivation operation. So perhaps if you look at the factorial of polynomials, I think for better record of people on the air, it's better to look at this. Yes. When you do derivation operation to this polynomial, it's straightforward to say you find the derivation of this, multiply this, plus the derivation of this, multiply this. It means you can analyze each polynomial in detail while multiply the other as a constant. So that's what this slide is going to share is this the observation of the entropy looks like the chain rule. You analyze one object and find the summation with another, and you find the detailed information of another object, and there are some constant multiplication. And for derivation, it's like the polynomial things, right? Then the next tree shows, it's given here. So the next slide shows you look at entropy. Entropy follows these rules and gives you the behavior once you do derivation, once you move from layer to another layer, move from one object to another. Then you will achieve this conclusion and say you can have a correspondence between the Shannon entropy and the derivation behavior of this operad over topological simplexes. Recall that the operad we call algebra, abstract algebra, how you compose things together. And topological simplexes is the thing you define n-dimensional distributions. So if we go back to the first part of this this lecture, we discussed there are two ways of thought. One is topological things, you know, the very, very detailed, you know, the derivation, continuity, connectedness, if there are holes or no holes, there are singularity or not, given the small, topological space. Another thing is, you know how to combine things together. And back to Hermann Weyl's time, he know there is such a thing, but he didn't point out that the information theory can combine these two ideas, right? And one comment perhaps made by me is, we look at this topological simplices. This is n-dimensional, when it's a finite number, n-dimensional simplices. But in practice, when we consider distribution, continuous distribution, like Gaussian distribution, like Rayleigh distribution, these things, we actually consider some topological things that goes beyond this n-dimensional simplices. That is studied in functional analysis called distribution theory. If you encountered that in your research, that was studied by Schwartz. So one distribution, the Gaussian distribution, the Rayleigh distribution, gamma distribution, they all follow very well-behaved, they all have some well-behaved patterns. Like the integral of all distribution is 1. The derivation of all the distribution always exists. You see the derivation of Gaussian is still Gaussian. It never diminishes. It's not like the polynomials that when we do a lot of multiple derivations, it disappears. Like when you consider linear, the second order derivative doesn't exist, or it's always 0. So, but this still hold. It says the derivation of the operad of topological space more than topological simplices. Once you consider the continuous case, you can simply replace its simplices by something defined in the distribution space. Okay, so probably we close here is I quote a takeaway from Dr. Bradley. He uploaded this paper 2021 very recently. Says that this entropy formula defines a derivation of this algebra and topology. And this is the rest part is more quantitative discussion. Says for every derivation, you will have the entropy times constant multiple. So I think here is everything of today's reading group lecture.
Thank you very much. Are there any questions, remarks, and so on?
I have a question.
Oh, please.
Ludovic speaking. Yeah. So thank you for your presentation. I think for me it was really interesting to bridge the different mathematical domain all together to give some additional information, additional understanding of what is happening. I have a question. So you showed that there is this bridge between algebra and topology for the entropy, use the entropy. But yes, where can you use this new knowledge to get some new results?
Okay, I can give you a simple example.
Yeah.
Say I want to talk about bananas. I say I have what would I do when I say I have 2 bananas? One way I say I have banana and a banana. Another way is I have 2 bananas. Both are fine, but if you understand things from the entropy perspective, the way I say banana and banana has less entropy than 2 bananas, right? Because banana and banana is in our domain is called repetition coding. You just send the things twice. It doesn't achieve the sum of entropy because you basically lost the entropy from another symbol. For example, if I want to say 3 bananas, I use 2 symbols instead of 3 symbols, but the 3 symbols send less information. So in this you can understand from channel coding is how to send the information more efficiently. Once you can organize the information in this chain rule way, it's highly effective than you organize things not follow this way, I would say.
Zeno, you have a question?
Yes, I have a question. There's now many other forms of entropy, for example, linear entropy, Tsallis entropy, and the mathematical form is not the same, but from the, I don't know, I think it has the same power as Shannon. Does it change in your way of your model?
Well, I would perhaps I didn't read the linear entropy, but I know there are different style of entropy, like the Renyi entropy, like the differential entropy. The difference is the topological things they are defined. For example, the differential entropy is defined over the continuous functions rather than discrete functions. That's what I said before the end of this talk. Said here, you define the derivation of the operator of topological simplices. This simplices is a topological object to define this n-dimensional, finite dimensional probability distribution. But once you go to infinite dimensional distribution, you probably want like the Gaussian distribution, like the relay distribution. They are continuous. Continuous means it's infinitely has infinite dimensional, like in the Hilbert space or in the distribution space. Then, based on that topological property, you would need this differential entropy. But they follow the same between this for this statement. For this statement, they say derivation of operad of topological simplices. Once you replace this topological simplices by other topological space, you would have different definition of entropy. That's my understanding.
Because the problem was to get rid of the logarithm, which has some problems. Does then the topology, and I think it can also be discrete. You don't need to do only continuous. So the question is, if you change the mathematical form, does it change your rules?
I don't think so. To be honest, I think I think the most important thing about definition of entropy is this log form things.
Yeah, but that's there's no log more in the other entropies. They have polynomials or whatever.
Oh, I would like to read your if you can some
Tsallis, for example, you look at Tsallis entropy, which is used. It's a sort of an approximation. If you take the log serious development, you can stop at some terms, and then you have the same entropy. You have the same properties as entropy, but you don't have no more the logarithm.
Okay. Okay, we can. I think we can.
Okay. Okay, thank you.
I just have a question, Zeno, on what you said. In this case, with this other kind of entropies, do you have the same rule as the one on the right of the slide?
Yeah, that's my question.
I don't think so, honestly, but
that's why I
so it will not work the same in that case. I suppose.
For example, in quantum information, they use very much linear entropy, which is just square root of square of some function.
The beauty of the entropy of Shannon is that this rule, in fact.
It's true. Well, thank you very much.
Yeah, thanks for your question. I will read this linear entropy further and see if there is also